Welcome back. This is Paul Walcher, and this will be our lecture on section 5.1. Getting very close to the end now. Today in this lecture, we're going to be talking about systems of equations. So section 5.1 is systems of linear equations in two variables. It's also just an introduction to the topic of systems of equations in general. We're going to start out with some definitions. A system of equations is a set of two or more equations that are considered simultaneously. That is, they're all assumed to be true at the same time. The solution set of a system of equation is the set of values for the variables that make all the equations true simultaneously. For a two-variable system that we're going to be looking at in this section, we'll generally express the solution as an ordered pair. For a three-variable solution, it would be an ordered triple, so you'd have three numbers separated by commas inside of a parentheses. So, for example, this system of equations, x plus y equals 5 over x minus y equal 1, all you're trying to do is you're trying to find a set of numbers that satisfies both equations. Now, this one you can probably find by inspection because it's not a very difficult system of equations to solve. What's a set of two numbers that adds to get 5 and subtracts to get 1? Well, you'll probably come up with 3 and 2 pretty quickly. Specifically, x has to equal 3 and y has to equal 2. So we generally express the solution not this way, but as 3, 2. One of the main reasons it's expressed this way is just so you get the connection. X has to be 3 when y equals 2. So the way you check a system of equations is you take these and plug them into both equations. 3 plus 2 equal 5, 3 minus 2 equal 1. Graphically, you can tell where a solution is going to be by looking for, well, let's graph them and see. This would be y equals 5 minus x, if I solve for y, and y equals, subtract the 1 over, add the y over, y equals x minus 1. If I graph both of those, five minus x x minus 1 if you'll notice here at this point 3, 2 is where the two lines cross, which shouldn't really be a surprise if you think about what graphs are. Graphs are visual representations of the solutions of an equation. So along this line is every solution of this y equal 5 minus x, and along this line is every solution of y equal x minus 1. The solution of a system of equations is a common solution to both equations, because both equations has an infinite number of solutions, but they only have one solution in common, a solution that solves both equations, and that's where the intersection is. So a lot of system of equations problems you could solve just by graphing both equations and finding their intersection. Your calculator even has a function for doing this. If you go down to intersect, the inputs are you have to tell it which curves you want. First curve, well, you just look up in the top left to see if that's one of them. It is. The second curve, that is the other one. And then you just have to tell it a guess, because it is possible to have multiple intersections, so you need to tell it the right one. And there we go, 3, 2. Now, solving by graphing is not a perfect method, though. The problem with solving by graphing is that sometimes it's hard to read off the exact value of a point. You might have a point at some fractional value like 3/7, 5/8. Or you might have an irrational number, an infinite non-repeating decimal. That would be practically impossible to read off of a graph unless your scale is very precise. So what do you do in those cases? Well, there are algebraic ways of solving systems of equations. So those are where we're going to put most of our effort. Here are some other properties of systems of equations. Systems of equations can have no solution, a finite number of solutions. Like we just saw, we had one solution in that last problem, or an infinite number of solutions. Just a brief example of each. Two equations with no solution might be x plus y equal 2 and x plus y equal 3. We haven't actually talked about how you would solve these yet, algebraically, but just looking at them, just analyzing what that means, I add the same two numbers together twice, I should get the same number both times. So if they sum to different things, they can't be the same. And if you look at their graphs, one will be y equal negative x plus 2, the other will be negative x plus 3. You look at their graphs, they would be parallel lines. Parallel lines have no intersection by definition. So it's impossible to have a solution, because a solution would have to be a common point on both graphs. Infinite number of solutions would be if it's literally the same line. Like 2x plus 2y equal 4. Well, if they're the same exact graph, then they're going to intersect in an infinite number of places, because they're going to intersect at every single point. So there's an infinite number of solutions. Now, college algebra, we treat this a little bit differently than you typically do in intermediate algebra. We actually write out the form of each solution. So we will be doing that, but we'll get to that when we get to that. The last bit of information on this slide is about what we call all the different cases. So you might see this in the homework. They'll ask you to solve a system and ask you to classify it. So, if a system has no solution, it's called inconsistent. A system with at least one solution, so that could be finite or infinite, is called an consistent system. And then you can break down consistent systems as independent or dependent. An independent system has a finite number of solutions. A dependent system has an infinite number of solutions. Technically, you could call an inconsistent system independent as well. Usually they don't ask you to classify an inconsistent system further, because if it's inconsistent, by default it has to be independent. At least with two equations anyway. Let's deal with the different methods of solving systems of equations. The first method we're going to look at, substitution. This is a fairly simple process. We've actually done some variety of it before. Where you do substitution, I'll just demo really quickly with the equation we started with, x plus y equal 5. X minus y equal 1. You solve one of the equations for a variable, and you substitute into the other. Doesn't matter which equation, so I will solve the first one for x. X equal 5 minus y. Then you take that, and you substitute into the other equation. X equal 5 minus y, so 5 minus y minus y equals 1. I just replaced x with 5 minus y, and now I got an equation in one variable that I can solve. 5 minus 2y equal 1. Negative 2y equal negative 4. So y equal 2, which we know is the y-coordinate of the solution. Back substitute now. So you take this value that you actually know and plug it into one of your previous equations in two variables. In substitution, you've usually already solved one for x, so that's usually the most convenient. But you're welcome to plug into either of these equations. It should work either way. So x equals 5 minus 2, which would be 3. X has to be 3, y has to be 2. You can plug them back into both equations. Yes, you should plug them back into all your equations to solve. So you got 3 and you got 2. And you're good. The first problem we're going to look at from the book is this system of equations. We have 4x plus 2y equals 16, x minus 5y equals 70. Now the instruction in solve a system was to solve one of the equations for a variable. You usually just solve for whichever one looks easiest. It looks really easy to solve for x in the second one, so that's what I'll do. X equals 5y plus 70. I'm going to take that, plug in there. So I'll have 4 times 5y plus 70 plus 2y equals 16. That'll be 20y plus 280 plus 2y equals 16. Move over the 280, 22y. That'll be 264. Now I do believe that goes in evenly. Y equal negative 264 divided by 22. Because that would be, let's see, 22 would go into 220 10 times, and that's just 44 more, and that's just 2 more times, so it'd be negative 12. So y equals negative 12, x equals 5y plus 70 equal 5 times negative 12 plus 70. That's negative 60 plus 70 equals 10. So the solution is 10, negative 12. And we can do a check. I should have really checked first. 4 times 10 plus 2 times negative 12 equals 40 minus 24 equals 16, and that's correct. And then 10 minus 5 times negative 12 equals 10 plus 60 equals 70, and we're good there too. Next we're going to look at exercise 39. Here I have 6x plus 4y equal 12 and 9x plus 6y equal 18. This one I wouldn't say either one looks especially easy to solve for anything. Just depends. Just pick one. So I haven't really solved for y yet, so I will solve the first one for y. 4y equal 12 minus 6x. So y equal 12 minus 6x over 4, which would be 12 divided by 4 is 3. 6 over 4 I could reduce to 3 halves x. I split it up into two terms, 12 fourths minus 6 fourths x, if you didn't understand what I did there. because you can't just reduce with one term. It has to be with everything on the top. Alright, so 3 minus 3 halves x, take that and plug it in for y. So 9x plus 6 times 3 minus 3 halves x equal 18. I will get 9x plus 18 minus 6 times, let's see, 3 times. The 2 would cancel with the 6, you get 3. 3 times 3 would be 9. So minus 9x equal 18. And look what we get. We get 18 equals 18. Now, this is one of the other cases other than a finite number of solutions. This is a consistent system because if you notice, we came down to something true. What this is saying is that this is true for an infinite number of solutions. By the way, the difference between infinite and no solution is that in infinite number of solutions, you'll come down to something like this: 18 equals 18, or 5 equals 5, or 0 equals 0. With no solution, it will come down to something that is not true, like 18 equals 19, or 20 equals 0. But if it is true, this means there is a solution, and there's an infinite number of them, and you should write their general form. How do you do that? Well, it's not too difficult. Basically, the idea with an infinite number of solutions is that one of your variables can be anything, any real number. So, we generally just let one of the variables be any number. I usually express it this way. One of the first variable is just x, but the second variable has to be calculated in terms of that. So one of the variables can be arbitrary, but the other one has to be calculated. So if the first one is x, the second one is 3 minus 3 halves x. Because we just solved for y. Y would have to be 3 minus 3 halves x. So for example, if x was 0, y would have to be 3 minus 3 halves times 0, 3. And if you plug that in, 0 plus 4 times 3 is 12. 0 plus 6 times 3 is 18. Also, let's say if I pick 2, then I'd have 3 minus 3 halves times 2. That would actually be 0. 2 times 6 is 12. 2 times 9 is 18. Just plugging in values for x, calculating this one, that gives me a solution. Now, I picked x to be arbitrary, but I could have just as easily picked y to be arbitrary. If I'd done that, I would need to solve for x in terms of y. So I just take one of these, solve for x instead. 6x equal 12 minus 4y. Divide by 6, x equal 2 minus 2/3 y. And that's what you'd put here. 2 minus 2/3 y. Notice if you plug in the same y coordinates, you get the same solutions. If you plug in 0, for y, you would get 2 for x. If you plug in 3 for y, you would get 2 minus 2. Yeah, you get 0 for x. So these both produce the same set of solutions. They just have different variables as arbitrary. But the key is that one of them can be any real number, the other one has to be calculated. One of the things you call them in statistics, something like this, is degrees of freedom. This has 1 degree of freedom because one of the variables can be anything, but the other is determined once you pick that. Online, sometimes they might write it like this, but more often they will say, if you have a dependent system, let's say x be a, in which case y would be 3 minus 3 halves a. Or if they said let y be a, then you'd have 2 minus 2/3 a. It's the exact same idea. It's just replacing a variable with a more general constant a. And that's fine, but I honestly prefer this notation just because, it's the x coordinate. I might as well call it x. It's the y coordinate. I might as well call it y. But you can call it whatever you want if you want to follow that notation. But that's what it means if it starts telling you to put a's in coordinates. This is exercise 36. I have negative 3x plus 5y equal 2 and 9x minus 15y equals 6. So I solve this by substitution. I'll just solve. Doesn't look like there's any special way to make this easier either way, so I'll solve the bottom one for x, let's say. 9x equals 6 plus 15y. X equal 6 plus 15y over 9. So, reduce everything by 3. 2/3 plus 5/3 y. Might as well just be 2 plus 5y over 3, but oh well. So negative 3, well that's convenient, times 2/3 plus 5/3 y. Convenient because you multiply the 3 through, it's just going to look at the fractions. Plus 5y equals 2. So that's negative 2 minus 5y plus 5y, 2. So that'll be negative 2 equals 2. Now that is clearly not true, so this is no solution. No solution is a bit harder to check. We saw with infinite number, you could at least calculate a solution and plug it in to see if it works. No solution, not so much. You could probably graph them and make sure that they're parallel lines, but other than that, there's not really anything else you can do. But yeah, no solution, you have to come down to something impossible. Negative 2 cannot equal positive 2. So, no solution. Let's talk about the other type of solving. The other solving method is called elimination. This is a very nice method in certain cases because it can get you to at least one value of the variable very, very quickly. The idea is that since both sides of an equation are equal by the addition principle, you can add the same thing to both sides of an equation. So you can actually add another equation to it. Because if I add, say, x minus y to this side and 1 to this side, well, technically I've added the same thing to both sides because this is equal this. So if you do that in this particular case, notice I will get 2x, but the y's will go away. The y's will be eliminated. So we get 6. But then, that's really easy to say then, x equals 3. Now, one of the variables is really easy to solve, and then you've got to take that and back substitute to actually find the other one. So you just take one of your equations. I'll take the bottom one. I'll take the top one this time. 3 plus y equal 5, y equal 2. Elimination can be very quick, but the key is they've got to be preconditioned for it to work. You have to have either your x's to be the same with opposite signs, so both 2x, but one's positive 2x, one's negative 2x, or both y, or both 7y, one's positive, one's negative. Because if you add them and they're not preconditioned, you're not going to eliminate any variables, and that's the whole point. Well, let's practice this. Start out with something simple. This is exercise 22. I have x minus y equal 3, x plus 3y equals 7. One thing you should always do on these problems is make sure you plug them in correctly. It'd be a shame to go through all the work and then realize you miswrote it. So this one, as if I add them, nothing would go away, but it's fairly easy to fix that. You can see my x's already have the same coefficient, so I'm just going to take one entire equation times -1. As long as I do it to both sides of the equation, it's still going to be equal. -x minus 3y equal -7. Don't forget to do both sides. And on the top I still have x minus y equals 3. Add down. I will have -4y equals -4. So y equals 1. Then I just need to plug that back in, so I'll plug it back into the top. X minus 1 equals 3, so x has to be 4. 4, 1 should be the solution. Certainly works for the first equation. For the second equation, 4 plus 3 would be 7. Yes. And you'd get the exact same result if you manipulated the y's instead of the x's. So suppose I took this thing times 3. That would have got me 3x minus 3y equals 9. And still would have had x plus 3y equals 7. Add down, you would have got 4x equals 16. So x equals 4. And then you would have plugged in and got y equal 1. I'm going to do 37 next. I got 2x minus 6y equal 10. Negative 3x plus 9y equal negative 15. Well, here, you see, if I want to solve this system, I probably got to do something to both equations. Like, for example, I could get both x and y to be 6 by multiplying the top one by 3, the bottom one by 2. But I think I'm actually going to do this instead. Top one's everything's divisible by 2, so I'm just going to divide everything by 2. I'll get x minus 3y equal 5. Bottom one's divisible by 3. So you get negative x plus 3y equal negative 5. Add down, you get 0 equals 0. This is an infinite number of solutions. So their form, well, let's just solve one of these. X equal 3y plus 5. So if y is arbitrary, x is 3y plus 5. That would be a perfectly acceptable solution. If you gave me that on a test, I would give you full credit. It just depends on which one they tell you to leave arbitrary on the actual homework. And if you solve for y, you get 3y equal x minus 5. So y equals x minus 5 over 3. So x minus 5 over 3 would be the other possible solution. And again, you can check them if you want. The way I do that is I just find a point and plug it in and see if it works. So if y is 0, x should be 5. And I mean, unless you just really screwed up, this should work out just fine, because I mean, you only have one equation. So 2 times 5 is 10, negative 3 times 5 is indeed 15. So we're going to do problem 62 here. A fruit stand sells two varieties of strawberries, standard and deluxe. A box of standard sells for $7. A box of deluxe strawberries sells for $10. In one day, the stand sells 135 boxes of strawberries for a total of $1,110. How many boxes of each type were sold? Well, this is an application of a system, and the difficult part, as always with application problems, is that you have to build your equations. But just look at what they give you. They told us how many boxes we sold, and notice that's what they're asking. They want to know how many boxes of each type, so those should be our variables. We have standard strawberries, which I don't usually use S's because my S's look quite a bit like my 5's. So let me say B for number of standard strawberries. See, my S's really do look a bit like 5's. Strawberries. And D for the number of deluxe strawberries. I think we should be able to work with that. Alright, they told us... Oh, I think we're talking boxes. I should say that. Let me go check the problem real quick. Yeah, a box. Okay. So boxes of standard strawberries, boxes of deluxe strawberries. Then they told us two things. They told us how much money we made from selling all our boxes, and they also told us how many boxes we sold. So that's going to get us two equations, because we know how many boxes we sold. Well, that should literally just be B plus D, because these are the two types of strawberries. If you look at B plus D, this should equal 135, because we sold 135 boxes of them. So B plus D equal 135. Then the other one, the other total they gave us was the total amount of money we made, which was 1,110. Well, these standard strawberries cost $7. Deluxe strawberries cost $10. How much money did we make from the standard strawberries? Well, each one got us $7, so our total money from the standard strawberries would be 7 times B. And our total money from the deluxe strawberries would be 10 times D. Yep. And then we know the total money from everything was 1110. So now I've got two equations. A system of two equations in two variables, which I can solve. What method do you want me to use? I'll use both of them. I'll just show them separately. You can use whichever one you want. I'll do elimination first. Probably the easiest way to do elimination, I would think. I'd have to either multiply B here by -7 or D by -10. I think I'm going to do -10 just because it's easier for me to do a multiplication by 10 than by 7. So that will get me times -10 would get me -10B minus 10D equal -1350. Add down, you will get -3B equal, let's see, that would be -240. then divide out the negative 3, and you would get b equals 80. Now b equals 80, 80 plus d has to equal 135, so that means d has to be 55. Let's see, I know it works in this equation, 80 and 55, but let's see if let's make sure it works in the second equation. 7 times 80 plus 10 times 55. 1110. Okay. Works out. This is the solution. So we have to have 80 boxes of standard strawberries and 55 boxes of deluxe strawberries to come out with this particular case of selling 135 boxes for a total of $1110. We're also going to do one of these motion and a current streams. The idea with motion and a current, whether you're a boat in a river or an airplane on the wind, is that your rate when you're in a river will be a composite of two things, because there's the rate of the river and then there's the rate of your boat. And usually the rate of the boat is considered as if you were in a still pool, so like there was no current at all. What would the rate of your boat be? Well, the idea then is your rate downstream is going to be your rate of the boat or the rate in still current. That's probably a better way of saying it. So whether you're a plane or a boat, the rate that the boat or plane would go if the current was completely still, no forward or backward movement, plus the rate of the current. So if you're in a rowboat on the river's flowing 5 miles an hour, you're rowing at what would normally be, say, 4 miles per hour. Well, if you're going downstream, your overall rate would be 9 miles per hour. Upstream would be the rate in still current minus the rate of the current. So, if your rowboat is going 5 miles an hour and the current is going 2 miles an hour, you would be still going forward at 3 miles per hour. If the rate of current is greater than your rate in still water, you're going to be going backwards. So, rate downstream, you get to add the rates. Rate in still current plus the rate of the current. Upstream, you have to subtract the rates. Rate in still current minus the rate of the current. In this case, I've probably got enough room to do this actually right here, so I will... got a fair amount of space over here. It's usually good to keep track of some of these things in a table. So I'm going to do 64. A boat on a river travels downstream between 2 points 20 miles apart in 1 hour. Return trip against the current takes 2.5 hours. What is the boat's speed and how fast does the current in the river flow? Well, let's say R equal boat speed, W equals, well, let's call it C. C equals speed or rate of current. Get rate, time, distance. So we get downstream, upstream, downstream between 2 points, 20 miles apart, return trip, so it's the same distance both times, 20 miles. Return trip against the current takes 2.5 hours. So 1 hour for downstream, 2.5 hours for upstream, and the rate, well, let's see, this would be R plus C, this would be R minus C. So let's see. Distance equal rate times time. So I can plug in for both of these. 20 equals R plus C times 1. And 20 equals R minus C. Oh, I actually forgot to solve the other one by substitution. I'm sorry. Oh, I really want to finish this one before I go back, so I will do this. It'd actually be 2.5 there. So, elimination, this would actually be pretty easy to do, because you could divide this 2.5 out, and you would have divide by 2.5, divide by 2.5, and I would have 20 equals R plus C, and 20 divided by 2.5 would be 8. So I'd have 8 equals R minus C. So 2R equals 28. And R equals 14. So boat speed was 14 mph. Speed of the current, well, that would have been, I gotta plug in, let's say this one, 20 equal 14 plus C, so C equals 6 mph. And of course, if you wanted to do substitution, that's easy enough. You could still do this, and then divide out the 2.5, and then say solve this one for R equal 8 plus C. Plug into the top one. 20 equal 8 plus C plus C. 2C equal 12. C equals 6. And then just plug into either of them. Plug into the top one again, you get the same thing. So 6 miles per hour for the rate of the current, so the rate of the stream. 14 miles per hour for the rate of the boat. If you go back to our previous problem, where I had B plus D was 135, and 7B plus 10D equal 1110. I just solved the top one for one of my variables, so D equal 135 minus B. 7B plus 10 times 135 minus B. 1110. 7B plus 1350 minus 10B equal 1110. Negative 3B equal negative 240. Taking the 1350 over. So B equals 80. It didn't get this. It's the same from then on because you just plug that back in here as well. Alright, I'll go ahead and set up one more, but I think I'm done solving. You can solve this one yourself, but I'll set up a couple more actually. 67. May have nightmares about this problem. We last saw this type of thing back in, let's see, I guess that was back in 1.5. Mixture problems are still the same though, it's just we can express them also as systems of equations. So we have different concentrations of acid. So, what are the concentrations of sulfuric acid in the original containers? We want to get a mixture that is 15% acid. And we know we had 300 milliliters of the first solution and 600 milliliters of the second. So let's say 300 milliliters of the first percentage plus 600 milliliters of the second percentage, so we'll just call that P. Looks like a B. P equals, well, it'll be 15%, so of 900, so it would be 900 times 0.15, because the total acid in the two ingredients is going to be equal to the acid in the result. And similarly, the other one says blending 100 milliliters of the first, so 100 of the first, plus 500 of the second, equals, well, you'd have 600 milliliters of 12.5, so 0.125. Now I've got a system of equations in two variables that you could solve to get your answer. I would say probably the first thing I don't know, it's up to you. I would probably divide out 100 from everything, so you'd have 3F plus 6P equal 9 times 0.15, and you'd have 1F plus 5P equals 6 times 0.125. But I mean, that's up to you. Something similar for this one down here. Biologist has two brine solutions, one containing 5% salt. How many milliliters of each solution should she mix to obtain a 1 liter of a solution that contains 14%? So I'll call this one X, this one Y. I know if I add them together, I have 1 liter total, and then my total salt, I have 5% of X is salt, I have 20% of Y is salt, so 0.05X plus 0.2 or 0.20 Y would equal the total salt in the solution, so that would be 0.14 times 1. Solve that system and you'd have your answer. And an interest problem. Remember, interest equals principal. Simple interest equals principal times rate times time. So he has two accounts, one paying 6%, the other paying 10%. How much did he invest at each rate? So I'll call his money invested here X, his money invested here Y. I know he put twice as much in the lower yielding account. So, let's see. Oh, okay, twice as much as in the other one. So that would mean X equals twice Y. And his annual interest is $35.20. Well, interest is principal times rate times time. Our principals are X and Y. Our rates are given. And our time, well, we're doing annual interest, so that would be over 1 year. So the interest on X would be 0.06 times X times 1. The interest on the Y, the 10% account, would be 0.1 Y. Total annual interest is $35.20. Those are your two equations. This one's tailor-made for substitution. Just plug in 2y for x and go from there. If you have other problems, I'll be glad to help. But I think that'll finish us off on the section. Next time, we'll look at systems of equations in more than two variables, like 3 or 4. Still be looking at linear systems, so it won't be that much more complicated. It does increase exponentially in work, though. I mean, there's no getting around it. It takes a while to do these things. I'll talk to you then.